Hello everyone, let's do the last set of questions, organic questions for the JAM 2019. So the first question says the correct statement or statements, so that means more than one answer can be correct, among the following is or are. So the first option is the secondary structure of polypeptide describes the number and type of amino acid residues. So this is not correct. Why? Secondary structure talks about alpha helix structure or beta pellate structures of the peptides. So it does not talk at all about number or type of amino acid residues. Okay, it just talks about how they will interact, what's the hydrogen bonding form, and what will be the most stabilized structure. Okay, the next is uracil is pyrimidine nucleobase. So if you remember, in DNA we have A binds with thymine. A binds with thymine through double hydrogen bonding, and GC, guanine, binds with cytosine with triple hydrogen bonding. Okay, so these two, A and G, adenine and guanine, they are purine, and T and C, they are pyrimidine. And in RNA we don't have thymine, we have uracil, so that is also pyrimidine. So option B is correct sentence, because it has asked uracil is pyrimidine nucleobase. Okay, so A and G are purine, T, C and U are pyrimidine. Okay, third one, natural fatty acids have odd number of carbon atoms. So you have to just remember they have even number of carbon atoms. Next is reaction of D-glucose with CaOH twice. Sorry, I have written this mistake. CaOH twice gives a product mixture containing D-fructose, D-mannose and D-glucose. So first let us understand the difference between glucose, fructose and mannose. So let me show you, that will be much better to show. So you are having D-glucose, okay. So D-glucose, the second carbon, this OH is on right side, third is OH on left side, other two both are on right side. Okay? In fructose, see, glucose is an aldose sugar, so top you have CHO, whereas in fructose you have top is CH2OH and second you have ketone group, so it is a ketose sugar. What happens to rest? 3, 4 and 5 have same stereochemistry. And in mannose is epimer of glucose at carbon number 2. So same like glucose, only at carbon number 2 the OH is on right side, the mannose has OH on left side. So they are epimer at carbon number 2. So when you react it with calcium hydroxide, when you react with CaOH twice, what happens? First step what happens is calcium hydroxide, this CHO gets reduced and this becomes oxidized to C double bond O, that becomes D-fructose, and it further reacts. So this CH2OH again becomes CHO, and this OH, this stereochemistry is changed, this becomes here, so you get D-mannose. So is the right answer with calcium hydroxide. These are the three products formed from D-glucose. So option D and B are right. Okay. So moving to the next question, the diastereomeric pair among the following options are. Okay, so for diastereomers, very important is you should have more than one chiral center, because if you have one chiral center then it can just have a pair of diastereomer. When you have more than one chiral center, then what happens is, at least for diastereomer to fulfill the criteria for diastereomers, at least one of the stereochemistry on the chiral center should be same, and at least one of them has to be different. Then what happens? The stereochemistry at one carbon atom which is same, that part will be superimposable. At the other stereochemistry, at the other chiral center where the stereochemistry is changed, that part it will be mirror image. So what happens? One part is superimposable, other part is mirror image. So the two molecules will neither, two stereoisomers will neither be mirror image nor will be superimposable. And what is the definition of diastereomers? Diastereomers definition is stereoisomers which are neither superimposable on each other and nor they are mirror images. So let us look at all of them and we will understand. See this molecule. These molecules are alkenes, so they will have geometrical isomerism, nothing to do with stereoisomer or enantiomer. So let us not worry about this one. This cannot be the right answer. Okay. Move to the next molecule. See, this is very interesting molecule. Here, if you look here on this carbon and this carbon, stereochemistry remains same. Here, methyl is towards the viewer. Here also methyl is towards the viewer. That means hydrogen is away from the viewer. Here also hydrogen is away from the viewer. What happens on the top where bromine is there? Now bromine, here bromine is away from the viewer and here bromine is towards the viewer. So this part is mirror image. If you could put them in front of each other, you can see that they both will be mirror images to each other. So this part is superimposable, this part is mirror image, and this part is again superimposable. So what happens? These two parts will superimpose over each other, but this part will not be superimposable because they will be mirror image. So they both will be diastereomers because diastereomers we define as stereoisomers which are non-superimposable, non-mirror images. Let us see if I have done more operations down. I have not done, so that's enough. Okay, let's see at option number C. In option number C, we have this one. Okay, so you have both stereochemistry, both OH and B are changed. You may think that if I just rotate it around, they may become superimposed, but it's not like that. You try to rotate it. If you rotate it, imagine if you just rotate it like that, then what happens? Br goes on top, OH comes on down, so they both don't superimpose on each other. Right now, this OH is towards the viewer, it is coming out of your screen. Okay, if I rotate it like this, I turn this molecule 180 degrees down, then what happens? This whole molecule is rotated. Then what happens? Both of them go away from the viewer, but this Br goes away from the viewer. Also OH goes away from the viewer. Okay. Okay, but they are not superimposable in each other. Now, but if you rotate this molecule 180 degrees like this, as I have shown there, okay. Let me show. Actually, I was searching for mouse. I am not able to find. Yeah. So if you rotate this molecule 180 degrees like this, then what happens? This whole part goes away. Then this OH comes this side. Then OH is away from the viewer and this Br is away from the viewer. You can see that these two are mirror images. So basically, what I am trying to say is, if a molecule has there which has multiple chiral center, and if stereochemistry at all the chiral centers are changed, then what you get is an enantiomer and not diastereomer. So if all the chiral centers you change stereochemistry, you will get enantiomers. So these two are definitely enantiomers and not diastereomers. Let us look at option D. Option D, again you can see very clearly what happens. This is the chiral center, so it is exact same stereochemistry. Here H is in axial position, and CH2OH is on equatorial position. Okay, so here stereochemistry is same. So one chiral center stereochemistry is same. Here also it is same. OH is in axial, OH is in axial. But here if you see, one OH is on equatorial position, here OH is in axial position. So what's the criteria for diastereomers? At least one of them should have same stereochemistry and at least one of them should have different stereochemistry. So here two of them have same stereochemistry and one of them have different stereochemistry. So option D is also diastereomer. So option D and option B are the right answers. Okay, this is very important. Please go through whatever I have written properly. The next question. The question says the reactions that result in formation of aromatic species is or are. So basically it says some intermediate is formed. Tell if that intermediate is aromatic or not. That's all it is asking. Okay. So you see what are the things used. One is SbCl5, one is AgBF4, one is sodium hydride, and one is sodium. Sodium hydride and sodium, they both are very powerful bases. Okay, they remove proton. And SbCl5 and AgBF4, they are called as superacids. They result in formation of carbocation, whereas here you will have carbanion. So let us look into it. What it does is basically Cl minus, it will abstract Cl minus. That's why it is superacid. It interacts with the conjugate base. It takes away the Cl minus and form SbCl6 minus. And because Cl minus is getting out, you are getting this positive charge. Now you have to look at this cyclopropylium carbocation. Cyclopropyl carbocation with a double bond. Okay, cyclopropene carbocation. Okay, and we have to look if it is aromatic or not. To find out if a molecule is aromatic or not, it has to fulfill few criteria. The first criteria should be cyclic and planar. So you can see it is cyclic. It is such a strain, it has to be planar. There is no other way. Okay. Then it says system should be conjugated. System should be conjugated. What we mean by that is this double bond is there, no? This should overlap. The pi orbitals on all the neighboring carbons of the cyclic system should overlap, and there should be movement of electrons. So you see here double bond was there, that means there is a p orbital, there is another p orbital, both of them had one electron. And when I am saying it is carbocation, that means this carbon is again sp2 hybridized. There is a p orbital which is vacant, and because it is vacant, it is positive charge. And then because they are cyclic, these are planar, they are next to each other, what they do is they start overlapping. So you can see all three of them overlap, and the two electrons which was there on only between these two atoms, now those two electrons are shared between all the three p orbitals. So if you want to show in the structures, you can show canonical structures like this. This pi bond moves here, you get positive charge. This moves comes here, you get a positive charge. So you get like this carbocation. Okay. So this is what you get as a species. So it is following all the rules. What are the rules? It is cyclic, planar, conjugated. Final, the C gives if it is aromatic or not. It should follow, it should have 4n plus 2 conjugated pi electrons, where n can be any number. It can be 0, 1, 2, 3, 4, anything. Okay. So how many electrons are there? Pi electrons are there which is conjugated in the pi system. So 2 electrons are there, you can see 2 electrons are moved. So when n is equal to 0, 4 into n, that means 4 times 0 is 0 plus 2. So plus 2 is equal to 2. So it becomes 2. So it is fulfilling Huckel's rule. This 4n plus 2 is called as Huckel's rule. Therefore this system is aromatic. Moving on to the next question. Again you have AgBF4. So basically it gives Ag plus interacts with Br. You know, many times when you want to do SN2 reaction, if a reaction is not happening, you add Ag plus, so that halide goes and conjugates with it, and then bromine gets positive charge. It is easy for it to leave, and it leaves, and you get this structure. Okay. So once this leaves, you are getting again a carbocation. So this AgBF4 is again superacid. You are getting this carbocation. Let us look at the criteria. Is it cyclic? Of course it is cyclic. Is it planar? Of course it is planar. Then is it conjugated? So we have to look at for the p orbital. This carbon has p orbital. It has p orbital. It has p orbital. Yes, it also has p orbital. This has p orbital. Yes, it has. When it has positive charge, it means it has a vacant p orbital, unhybridized p orbital, and other two also have. So they all overlap, and then electrons are being shared like how it is shown here. Now final, the rule is it should follow Huckel's rule, 4n plus 2. What are the number of electrons here? 1, 2, 3 and 4. So it is rather following 4n rule, where n is equal to 1. When n is equal to 1, you get 4 electrons. So for n, if it is following, it is called as anti-aromatic, much more unstable than non-aromatic system also. Aromatic are much stable than non-aromatic system. Anti-aromatic are very unstable. So it will always try to avoid the anti-aromaticity. So what will happen? It will get puckered up. This will come up so that conjugation is lost. System will never be an anti-aromatic. Whenever anti-aromaticity comes, it will try to be non-aromatic by losing its planarity so that orbitals don't overlap. So this is not aromatic. Okay. Moving on to the next question. Now you are using sodium hydride. Sodium hydride is a very powerful base where H minus acts as a base. It takes a proton. It's a non-nucleophilic base. It will never attack any carbonyl center. Okay. So this H minus goes and attacks this proton. You get negative charge. Why negative charge? Because see, to remove proton from hydrogen is very tough. But if negative charge stabilized, then it can be removed. You get negative charge. You can see this negative charge is stabilized over C double bond O through minus R effect resonance. You can see very clearly. Okay. Now we have to look at this system. Is this system aromatic? So is it cyclic? This part only I am looking at this part which I have circled there also. Okay. So if I look at that, then what happens? You can see it is cyclic, planar, conjugated also because this negative charge there. So this p orbital has electron which will overlap with this. But number of 4n plus 2, is it following? So number of electrons are 4. So again it is following. It is not following Huckel's rule, it is following 4n rule, so it is anti-aromatic. Final, the D if you put sodium against a very powerful base, it removes proton, you get negative charge. This is very stable. Why? Because you are having aromatic system. See, everything it follows, cyclic, conjugated and planar and conjugated. Why? Because this negative charge is there. This orbital containing negative charge will overlap with this p orbital, with this p orbital, this p orbital and this p orbital. So all the neighboring atoms are overlapping with their orbitals. So you can see this negative charge coming here, here, here. So it is conjugated system. And number of electrons, how many are there? 1, 2, 1 pi orbital 2 electrons, another pi orbital 2 electrons, 2 to 4, and negative charge means 2 more electrons, that is 6. So it is follows 4n plus 2, that is 6 pi electrons. Therefore it is aromatic. So the answers are option A and D. Next question. Based on the information given below, the isoelectric point pi of lysine is. So what is isoelectric point? See, if we have amino acid, amino acid is basically this. Okay, we are having basically this. H is there, R is there, then you are having COH, and you are having amino group. Okay, and you are having amino group. So they don't stay like this. Why? Because COH is a acid, NH2 is a base. So what happens basically is, not able to rub it. Yeah. So you are having NH2 here. So what happens is this NH2 takes proton from COH and becomes NH3 plus. It becomes NH3 plus, and COH becomes like this, NH3 plus, and COH becomes COO minus. So this is called as Zwitter ion. Zwitter ion means in the same molecule it is neutral. Okay, same molecule it is neutral, but it has both positive and negative charge. That is called as Zwitter ion. Okay, that is called as Zwitter ion. So in amino acid, imagine if you put lot of acid in it. Let us look at some molecules. One second. So what I was saying is, you get Zwitter ion like this. See, this is too tough to use this mouse. Okay, so you are having COO minus and you are having NH3 plus. Don't have a mouse here. I'm sorry, I didn't have mouse. Now I have proper mouse. Let us stop once again. So you are having deuterion something like this. Okay, so there is a carbon here. You are having COO minus, and NH2 picks a proton from this COH and it becomes NH3 plus. NH3 plus. And you are having your H here and you are having R here. Imagine if you put lot of acid, that means lower pH, then this CO minus will pick up proton and become COOH. Now it is no longer deuterion because it is having only one positive charge. Deuterion means it has to be neutral and it should have both positive and negative. Imagine if you put lot of base, you put lot of NOH in it, then what happens? This again, this COH will be lost, it becomes CO minus. Also this NH3 plus will lose the proton and it becomes neutral NH2. Right, because you are putting basic media, so it becomes NH2. Now what happens? You are having negative charge, it is no longer deuterion. So what is Pi? What is isoelectronic point? Isoelectronic point is that pH where you find deuterion. Okay, where you have deuterion. Now if normal amino acids are there, generally your isoelectric point will be around 7 pH because it is neutral where both of them will be present. But we may have something like lysine. Now lysine has extra NH2. Apart from this CH, it has extra NH2. So for them to find out the isoelectric point, you have to do little more stuff. So for that, what you have to do is you have to look at the species where deuterions are involved, and that pKa you have to round about. So this formula about general pKa is pKa1 plus pKa2 by 2. What is this pKa1? What is this pKa2? When you have general amino acid, see here amino acid, this was at neutral, so pKa2, so here you have put more of base, so this proton is lost and you get NH2. So here also deuterion was involved, and here pKa1, when you are putting more of acid, so that this becomes COH and this becomes NH3 plus, so here also deuterion is involved. So you have to look at the pKa's values wherever deuterion is involved. So here both front also, behind also deuterion is involved, so you have to take average of them. Whereas when you look at this lysine, so what happens? Here it is not a deuterion, okay, this is not a deuterion. This is deuterion because you are having minus, you are having plus. Now look here. So pK2 here is not deuterion, but pK2 will be used because it is involving one of the species which is deuterion. So this pK2 we have to use. pK3 also we have to use because from deuterion you are getting this. pK1 shall we let us see. So what is happening here? It is not deuter. What you are getting is also not deuterion. So will not be involving pKa1. Will be involving only pKa2 and pKa3, and will take average of that. So it will be pKa2 plus pKa3 by 2. That comes to 9.1 plus 10.5 divided by 2, that gives you 9.8. So now it becomes very easy. If you remember, whenever you have to find out Pi, just draw all the structures and then look whichever in whichever Ka value deuterion is involved. So that deuterion may be in the product form or the reactant form, but if it is involved, that pKa you have to take and then you have to add and do the average of it, right? Moving on to the next question. This is very simple. So you are having R2-methyl 1-butanol has specific rotation of 13.5 degrees. Specific means it is a concentration is given, and specific rotation of 2-methyl containing 40% S enantiomer is how much they are asking. So I am saying you don't have optically pure compound. If it was only R, it was plus, but now you have R plus S, where S is 40%, that means R was 60%. So how much it is? So just simple calculation. So you have 60% of R and 40% of S. So 60% of R value. What is R value? So you know it is plus 13.5. So if R value is rotatory is plus R plus value, that means it is dextrorotatory. So that means S will be levorotatory. So if R value is plus 13.5, S value will be minus 13.5. So 60% of plus 13.5 plus 40% of minus 13.5. So it becomes 60 by 100 into plus 13.5 plus 40 by 100 into minus 13.5. You do that, you will get 2.7. As simple as this. Okay. Last question. The number of Gauss-butane interaction in the following compounds is. So you are having this molecule. It is asking you how many Gauss-butane interactions are there. First, you should know what is Gauss-butane. So imagine this is the butane 1, 2, 3, 4. So when you draw like this structure, the Newman projection formula, the two bulky groups, when they are 60 degrees to each other, it is called as Gauss interaction. So what I have done here is, this part is there, no, I have just turned it like that. So it was in plane. This CH3, this bond and this H, they were all on the screen what you are watching right now. So what I am doing is I am pulling it up so that CH3 comes in front of me. These both hydrogens coming in front of me, and this whole thing is going back. So when that happens, this CH3 is coming towards me, these two hydrogens coming towards me. So it's kind of coming out, but I cannot show coming out of the board, so I am showing planar. Then this behind part I have shown like this. So this part I am not rotating, and behind part I rotate 120 degrees so that CH3 comes in place of H, this comes H, this get here. So you can see here, this is 60 degrees, this is 60 degrees. So these are the two Gauss forms present in butane. Now it is asking for this cyclohexane, but how many Gauss-butane interactions are there? So you know, when it is cyclohexane form, it can flip. So you are having this cyclobutane, you are having one methyl in axial, another methyl also in axial. They both are above the plane, so it is cis 1,2 dimethyl cyclohexane. Okay. So they have drawn here, but sometimes they can just ask you cis 1,2 dimethyl. So this is cis. So one is axial, one is equatorial. So it will flip. I should have not drawn this double-headed arrow. I should have drawn this equilibrium sign. Okay. Then when you flip, now this goes down. So this comes down here. So position 1 has come here. This lifts up and this comes here. When you flip, what happens is whichever substituent was in axial position goes to equatorial. Whichever was equatorial goes to axial position. And but if they are above the plane, it remains above the plane. If substituent is below the plane, it remains below the plane. So when I am flipping it down, so this becomes here. So here see what happens, CH3 was in axial position. It comes to equatorial position. This H which was in equatorial position goes to axial position. Similarly here, this equatorial position goes to axial position. This axial position goes to equatorial, axial position goes to equatorial position. Now these are the two structures, flipped structures. Now we have to look if Gauss-butane interaction is there or not. So if I just draw Newman, so what happens, you see here, it is like this, same like butane, tuck, 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 right? It is like this, like this, like this. What is on top? CH3, and this side your R group is there, and this side your H group is there, right? Front, what happens here again? This is H, this is R, this is CH3. So if I rotate it like this, like how we have shown in butane, this is the bond. So that bond I am not showing. So here what happens is, you are having H down, you are having CH3, I should draw like this, maybe CH3 this side, and you are having R prime this side. So what happens, you are getting this Gauss interaction. Similarly, if you look here, then what happens is, this CH3, H and R. So CH3, H and R you have drawn like this. Here behind part you are showing CH3 on this side, R on this side, and H, R on this side, and H on this side. So you are having again 16 degrees interaction. So two Gauss-butane interactions are possible, as you can see. So this is the answer. That's it for today. Thank you very much.